Welcome to Messi Pupen online course on fluid flow operations. In this lecture, we will discuss about the one dimensional flow as part 1. In the previous lecture, we have discussed about the what is that circulation, rotation, and also what should be the relationship between circulation, rotation, and also vorticity, all these things. Now, in this lecture, for a particular one dimensional flow, how the fluid will be behaving, and also what should be the continuity equation for one dimensional flow whenever fluid is flowing through a certain conduit. Let us see that first, that what are the basic equations of the fluid flow. So, if we say that the representation of the fluid flow includes these following basic equations by which you can actually represent the fluid flow phenomena, and also how the fluid actually will be facing different forces, and how these forces will be calculated based on these principles. Generally, main three basic equations of the fluid flow are there. One is called principles of conservation of mass flow, which is known as continuity equation, and another one is called principle of conservation of energy, and this is called as energy equation, and finally, that principles of conservation of momentum, here this is called the momentum equation. So, by this basic three main equations you can express the fluid flow operations. Except these three equations, some other supplementary equations are required to solve those equations. In this case, like law of thermodynamic properties, like to analyze the compressible fluid flow along with these basic equations, and another is to represent the gases or flow of gases. There, of course, you have to know the physical properties of the gases, because whenever it will be flowing through the conduit at a certain pressure and temperature, its physical properties will be changed. So, in that case, equation of state for that particular pressure and temperature to be represented, and along with these basic equations and with this equation of state of that gases, you have to express the phenomena of this gas flow there. There are two types, one is compressible, another is incompressible fluid. Already we have discussed in the earlier lectures. There are other several types of fluids also there. So, mainly compressible and incompressible fluids. Though compressible means those will density will be changing with respect to pressure and temperature, and it is called compressible like gases, and incompressible where the density will be remain constant. So, it will be compressible like water and other liquid also. And except this of course, compressible and incompressible fluid, there are other several different types of fluids are there. Now, we have already discussed in the previous or earlier lectures. They are like viscous liquid, non-viscous liquid. Even you will see that there are Newtonian and non-Newtonian liquid. So, whenever you are going to express all those phenomena of these fluids, whenever it will be flowing, these basic equations along with these physical properties of the liquid or fluid, you can say that gas, liquid, and other type of liquid you have to consider there. Now, if we recap on this one dimensional, two dimensional and three dimensional flows, that we have already discussed in the previous lectures, that what is that one dimensional flow, how it is actually being represented, then there are what should be the two dimensional flow and how this three dimensional flow also to be represented. So, in that case one dimensional flow there we have discussed that the liquid flowing in a tube in terms of average velocity, the flow has a velocity component in one direction. So, those type of flow will be called as one dimensional flow, and that one dimensional flow will be represented by u is equal u as a function of only one dimensions, like if it is in the x direction it will be only x as a function of x, and parallelly you have to consider that the time also, this is also depends on time. If it is steady state operation, then there will be no time consideration, but if you are considering that there will be a variation of this any fluid parameters in the particular direction, then you have to consider time also. So, in that case if we are considering that velocity of the fluid in the one direction, then it will be u as a function of u and t along with time. So, this is one important, and then another is called two dimensional flow, like liquid running between two parallel plates. In that case only two dimensions are considered, and there will be what is that cross cut vertically to the plates and parallel to the flow. So, in that case the velocity of the fluid will be represented as a function of spatial coordinates like x, y and also the time. So, it will be u as a function of x, y and t. Similarly, in the y directional flow for that particular fluid, then it will be represented by v, and then v also will be represented by x, y, z, because this u and v both will be changing spatially. That means, here with respect to what is that location, or you can say that distance also. So, that is x, y and z. So, in the x direction at a particular location from this origin to a particular distance, what will be the velocity? Of course, this velocity will be changing, and v also will be changing in the y direction. Similarly, for three dimensional flow, if suppose a ball that is flying in the air, that I have given this examples also earlier in the lecture, that in the air then you will see that flow around a moving ball in the sky, what will happen? You will see there will be a velocity components in x, y and z direction. So, in that case the velocity of that that means here around velocity of air around that particular object, then the velocity of that particular fluid will be represented by u, v and w in the x, y and z direction, that is three dimensions. So, they are of course, all these three dimensions will be a function also again on the x, y, z and also with respect to time. So, three dimensions, two dimensions and one dimensional flow here. Now, whenever we are considering to express the what is that continuity equation, that is called conservation of mass, we have to consider in one dimension, two dimension and three dimensions also. So, we have to first derive what should be the mass conservation equation, and that will be called as continuity equation. What is the principle of that conservation of mass flow? Suppose if you consider a flow of fluid between two sections here as shown in your figure in the slides, that if you are considering the fluid between two sections here, section 1 and section 2, that means see here these sections and here these sections, and the fluid will be flowing through these sections. Let the cross section area of these sections will be as A1 and A2, and in this case if we consider that velocity be V1 and V2 through these sections A1 and A2 respectively, then the conservation of this mass flow can be represented as that the rate of inflow of fluid mass between sections 1 and 2, how much that is liquid rate of inflow of fluid mass, this between sections 1 and 2, and rate of outflow of fluid mass between section and 1 2, and also what should be the rate of store of fluid mass within the sections 1 and 2. Now, if we relate all those things, like what is the inflow rate of fluid between these sections, and if it is considered as inflow I here, and also the outflow as O here, and the store of the liquid within these sections, that if it is, then you can simply say that I will be equals to O plus S here. Like this, that means inflow rate of inflow of fluid mass. This is of course with respect to time, not like that at steady state. We will consider that at steady state conditions also. If suppose the rate of inflow of fluid mass between sections 1 and 2, that will be equal to rate of outflow of fluid mass between section 1 and 2 plus rate of store of fluid mass within sections 1 and 2. You will see, suppose if any from any suppose any what is that pan, from any pan, from the top the if liquid is supplied at a particular rate, suppose V 1 velocity, or volumetric flow rate suppose Q 1, and the fluid is out like this from this pan, it will be suppose at V 2, and here the volumetric flow rate is Q 2. Here the cross sections of this pan will be same. So, in this case, if suppose this the flow rate Q 1 and Q 2 are same, then you will say that there will be no storage of water inside the that means there will be no increasing of that storage of liquid in the pan, inside the pan, there will be no that will not happen here. So, in this case, see, very interesting that if suppose Q 1 is greater than Q 2, volumetric flow rate of inflow is greater than Q 2, then you will see with respect to time the height of the liquid level inside the pan will increase. So, that is called with respect to time how the liquid will be storing inside the pan or in a conduit. But if Q 1 and Q 2 both are same, then there will be no increase of this level of liquid inside the columns, and it is called steady state. Then there will be no storage of fluid mass within these sections 1 and 2. So, that is why if we are having this storage, then you have to consider here, and if you are not having this, then it will be simply 0. So, the rate of conservation, that is principle of conservation of mass, will that will be represented by this equation. So, rate of inflow of fluid mass between sections 1 and 2, that will be equal to rate of outflow of fluid mass between section 1 and 2 plus rate of store of fluid mass within sections 1 and 2. Now, if suppose there will be no storage of liquid inside the pan or in a conduit, then simply you can say that will be steady state operation. With respect to time, there will be no storage of liquid inside the tank. So, it will be steady state. So, this will be coming that only the inflow and outflow will be same there. So, this is called the continuity equation. This is called continuity equation in the one dimension or one dimensional steady state flow. So, mathematically we can simply say that inflow will be equal to outflow, that means rate of inflow of fluid mass between sections 1 and 2 will be equals to rate of outflow of fluid mass between section 1 and 2. So, this is inflow and this is outflow. Now, how we can represent this rate of inflow of fluid mass? Suppose here this is the section 1, this is here the liquid is in, and liquid out here, that means here inflow, this is outflow. Now, in this case what will be the inflow rate here? If we consider that mass of the fluid as m, then rate of change of mass, that is rate of inflow of fluid mass, that will be equal to d m 1 by dt. Similarly, at the outlet the rate of outflow of the fluid mass will be equal to dm2 by dt. Okay. Now, what should be that dm1 by dt, that what is the rate of inflow of fluid mass? How? Mass you have to consider in terms of velocity here. So, what will happen? Mass will be equals to density into volume. Now, density is density of the fluid is rho, and volume will be equal to cross sectional area if it is A1, then velocity if it is V1, then A into V1, that will be your volume per second or per time, that will be equal to then what will be the rate of mass inflow there. And similarly, rate of mass outflow will be equal to similarly rho into A2 into V2. Now, as per this equation at a steady state condition, then simply we can equate these two rate of mass between sections 1 and 2. So, hence from this law of conservation we can write simply that rho into A1 into V1, that will be equal to rho into A2 into V2. This is your that means called mass rate of flow, that will be equal to constant here. So, this is as per continuity equation, very interesting that the rate of inflow of fluid mass always will be same with the outflow rate of fluid mass. Okay. So, mass rate of flow will be constant. This is the mass conservation equation here, and it is called as continuity equation. Now, very interesting that if we see that this product of this rho A1 into V1, that will be equal to rho A2 V2. Now, for incompressible flow, this rho will be constant, rho may not be 0, rho will be constant. So, in that case rho from the both sides we can omit or cancel it. So, it will be A1 V1 will be equal to A2 V2. Simply A1 V1 will be equal to here A1 V1, that will be equal to A2 V2. What does it mean? The product of the cross sectional area and the velocity through these cross sections will remain same. So, here suppose if any phi here cross section is higher than this cross sections, what will happen? Then as per conservation of flow, since it will be remain constant, then mass flow rate should be remain constant, then where the cross section will be higher, then velocity should be lower, whereas cross section will be lower, velocity will be higher. That is why we are getting that different velocity whenever the fluid will flowing through the narrow tube and the coarser tube. So, in that case larger diameter tube, the velocity will be lower, whereas the narrow tube, the velocity will be higher if you are supplying the same flow rate of liquid through these pipes. Another interesting point that as per this continuity equation, if it is unsteady flow, then how we can represent this continuity equation. Let us consider that figure again. Here this A1 is the cross sectional area, and through which the velocity of the fluid is V1, and the cross sectional area in the section 2 it will be A2, and the velocity through this cross sections will be V2, and density at this cross section it will be rho 1, and here it will be rho 2. And in this case if we consider that the mass of the fluid that enters through this control volume through this sections 1 and within this sections 1 and 2, or we can say that phase AB here, AB in the small time delta t, then we can write this equation MIL, that means here mass flow rate, that is inlet, that will be equal to what? How to represent this here? This is given rho into AV minus rho dou L into rho AV into delta L by 2 into dt. What is this here? Very interesting that before going to these sections, there will be mass flow rate rho AV. Whenever it will be coming out from these sections, there will be change of that mass with respect to length. So, it will be dou L into rho A B, this is mass per unit time, then if you multiply by delta T, then within that particular time what should be the mass, and since the length of this control volume is delta L, then average length will be equal to delta L by 2, and you will get then finally this will be your what is that, the change of mass with a small time of delta T. So, it will be MIL. Similarly, mass of fluid that leaving the control volume through the phase DC in small time delta T, it will be represented by this here. Here the initial liquid, it will come rho A B into delta T plus rho into dou L into rho A B into delta L by 2 at time this sections, that into delta T. So, here this will be your outflow mass flow rate. Similarly, we can write then what will be the then rate of increase of the mass of this control volume within this short time delta T. So, increase of mass will be delta M. So, this delta M will be equal to what is the inflow and what is the outflow. If we subtract this in outflow from this inflow, we can get the increment of the mass flow rate there. If there is a storage in a suppose fluid conduit, whenever fluid will be moving with a inflow will be higher than the outflow. So, there will be what is that, increment of this fluid, but that increment with respect to time. So, that is why this delta M with respect to time within a short period of time, it will be MIL minus MOL. So, we can substitute this MIL from this equation here, and then you just substitute it, and then MOL, then you substitute this MOL here in this form. Then finally, after simplification, you can get this minus dou L rho A V into delta L delta T. So, this is your increment of the mass element within a short period of delta T. But increase in mass of the control volume in terms of delta T is equal to what? That increment will be equal to what? Delta M is equal to rho dou T, that is simply rho A into delta L into delta T, that control volume. This is your control volume element, and this is your rho, this is the density. So, density into volume, this will be your mass, then this mass per unit time rho dou by dou T, and within a short period delta T, it will be represented at this increment of this mass. Now, therefore, we can equate these two things, this expression with this expression. Okay, since both are same delta M, then therefore, we can write simply this will be is equal to that means this one here, this is this one, and this is nothing but this one. If we equate this, then we can represent then what will be the continuity equation for the one dimensional unsteady flow, and it is coming that simply here dou T rho A plus dou L into rho A B is equal to 0. So, this is your continuity equation for unsteady flow. In this case, you will see that this rho A is the is changing with respect to time. So, since if A is changing, then of course, if rho and A both will be changing accordingly, then what will be the mass here, it will be changing with respect to time, and here also it will be changed. Now, if rho is not changing for incompressible flow, then you can simply say that dou A by dou T, that will be equal to dou L into A B, that will be equals to 0. But if suppose the conduit or pipe, if there is a fluid is flowing through the pipe with uniform cross sections, then you can say that A will also be taken out from this equation, then simply dou by dou T into rho and dou L rho V. So, this rho and V both will be changing, but if there is a uniform cross sections, then there will be no change of A. But if there is a cross section change, then of course, you have to consider here. Let us do an example for this continuity equation for understanding. Now, a pipelines tapers from 8 centimeter diameter to 4 centimeter diameter. Then the quantity of water that flowing through the pipe, it is given to you like 0.1 meter cube per second. So, within this flow rate of water, if it is flowing through the pipe and that pipe is tapers from 8 centimeter to the 4 centimeter like this here, this is 8 centimeter and this pipe is tapered to the 4 centimeter and here 8 centimeter. Now, see here cross sectional area is varying at this location and at this location, here 8 centimeter and 4 centimeter. So, it is obvious as per conservation equation that velocity of course, will be different. Here some velocity will be there and here velocity will be some there, and here cross sectional area let it be A 1, here it will be A 2. And since it is water, it is compressible fluid, incompressible fluid, then you can say that simply here A 1 as per mass conservation of equation or continuity equation, simply A 1 will be is equal to A 1 V 1, A 1 V 1 will be is equal to A 2 V 2, that is here, and that should be is equal to volumetric flow rate. So, Q will be is equal to what? A 1 V 1 equal to A 2 V 2. Now, question is that from this conservation equation, then what should be the discharge and the average velocities at these two sections. If you know this volumetric flow rate, then simply you can calculate what should be the velocity at this section, since you know the cross sectional area, because cross sectional area you can calculate from this diameter of this pipe. Simply cross sectional area A 1 will be equal to what? Simply pi by 4 into d 1 square, and A 2 will be equal to similarly pi by 4 into d 2 square. So, this is your cross sectional area. So, if you substitute this d 1 and d 2, you can simply get this A 1 and A 2. Similarly, how can I then calculate this V 1? V 1 is, since we know that Q will be equal to A 1 into V 1. So, V 1 will be equal to Q by A 1. Q you know that is 0.1 meter cube per second, and A 1 is calculated by this equation. Then simply you can calculate what should be the V 1, that will be 20 meter per second. But before going to calculate this, be careful all the dimensions to be considered in a particular system, not like that mixed system will be there. Here suppose MK system and here SI system. So, always should be same system like SI system. Here in this case 8 centimeter, you have here it is given flow rate is given meter cube per second. So, you have to consider this centimeter, or you have to convert the centimeter to meter. Then after substitution of this d 1 here, you have to calculate A 1 and A 2. After that you can divide it Q by A 1, then you will get 20 meter per second. Similarly, since this conservation of equations follows here, so Q will be equal to again A 2 V 2, the same flow rate in this sections also. What will be the flow rate here in this sections? That flow rate of course will be in this section also. So, in this sections what should be the V 2? Say V 2 will be again then Q 2 Q by A 2. So, it will be again as per substitution of this A 2 value, here it will come 80 meter per second, 80 meter per second, whereas here in this case it will be 20 meter per second. So, interesting that here V 1 is very less, whereas here V 2 is very high. That means, here see smaller cross sections will give you the higher velocity and larger cross sections will give you the lower velocity. So, this is the example that follows this continuity equation here. Similarly, if suppose any water flows in a 6 centimeter diameter pipe with a flow rate of 0.06 meter cube per second. The pipe is reduced to the diameter to 2.8 centimeter here, 6 centimeter to 2.8 centimeter. Here also you can get the same, the velocity at this sections will be lower, whereas velocity at this sections will be higher. So, in this case calculate the maximum velocity in the pipe. Also calculate the maximum mass flux, assume that uniform velocity profiles will be there. So, in this case maximum velocity in the pipe will be there, where cross sections will be lowest, where the diameter is the smallest. So, in that case 2.8 centimeter diameter sections will give you the maximum velocity. So, as per this q is equal to AV formula, then you can simply substitute this q value as 0.02 and cross sectional area this pi r square you can say into V2, or you can say pi d square by 4 also, either one, and then V2 will be equal to what, 32.5 meter per second, and the mass flux will be equals to m dot, that will be equal to rho into q, mass flux, that means here mass per unit time per unit cross sectional area, that is called flux. So, flux is defined as mass per time per area. So, this is your flux. So, here this flux, mass flux will be calculated as rho into q. What is that? How it is coming? That means, here dimensions dimensions of rho is kg per meter cube, and what is that? And q is here rho into q. Q is the volumetric flow rate. So, this will be meter cube per second, So, it will be what is that? Here meter cube cancel, that will be equal to kg per second, that will be your mass flow rate. Now, this mass is per unit cross section of that. So, this will be your, if it is per unit cross section area, if it is 1, then you can simply calculate what will be the flux. So, mass flux per, that means per unit area, here will be equal to m dot per unit area, that will be rho into q, that will be equal to 20 kg per second. Now, you can practice also one example here, the calculate the velocity if 10 meter cube per hour of water flows through a 100 millimeter inside diameter pipe. If the pipe is reduced to if reduced to 80 millimeter here inside diameter, then what will be the velocity there? The same way you can try once. Here 10 meter cube per hour, you have to convert it to meter cube per second by dividing 3600, and 100 millimeter to be converted to meter, that means you have to divide it by 1000s, then you have to convert it to meter, and here also you have to convert it to meter. Then you have find out the cross sectional area in this for this diameter and also for this diameter, and from those part then what should be the velocity, you can simply calculate it here, and finally you can get this answer is 0.55. Try once yourself. Now, continuity equation in 3-dimensional flow. In this case, consider a fluid element of lengths dx, dy and dz as per diagram here shown. Here, if we consider this fluid element, 3-dimensional fluid element, and it will have this face like this A, B, C, D, and here E, F, G, H, these two sections, these cross sections, here also another cross sections here A, E, H, D, and in this cross section B, C, G, F. These are the cross sections of this fluid element here. Now, rectangular fluid element we are considering here. So, in this case, if we consider this phase, you will see there will be a certain length of this rectangle here. What is this? What is the length of this? This will be dz. In this direction, it will be this is z directions, and this is y direction, and this is x direction. So, this what will be the length of this? This will be dy, and this will be your dz, and what is that? This will be your dy, and this will be your dz. So, this what will be the cross section of this area? It will be what? I think simply dy dz. Now, question is that suppose that if a velocity in this suppose u, v and w are the inlet velocity components in this x, y and z directions, and if we consider the mass density of this fluid element is rho at a particular in state, then what will be the fluid entering to the particular phases? Consider these phases first, like A, B, C, D. Suppose if we consider here the direction of the flow in the x. So, the fluid will be crossing these cross sections and it will be leaving out from these cross sections. So, in this case mass of fluid entering the phase A, B, C, D, that is called inflow of this mass, that will be calculated as mass density into velocity in the x direction into area of that phase A, B, C, D. So, this will come as mass density is rho, velocity is suppose u in this x direction u, then area will be equal to what is that, length into breadth, that will be dy dz. So, we can say rho u dou y dou z here. So, then mass of fluid that leaves the phase E f g h, that is called outflow, will be represented by this here rho into u into dy dz or del y dou y dou z, plus you will see whenever it will be flowing out from these sections, there will be a change of mass flow rate or velocity through these sections. That is why that velocity in that x direction, how it will be changing, that will be changed with respect to x. So, it will be dou rho u dou y dou z divided by dou x. So, in that case finally, the mass will be changed with respect to x here, it will be dou rho u dou y dou z divided by dou x. So, this is your mass of fluid that leaves this phase at this particular x direction. Then if we know this inflow and outflow in the similar fashion that we have already discussed, then rate of increases in mass in x direction, then it will be outflow minus inflow. What will happen then? If you substitute this outflow as this one that we have shown here, this is the outflow, and this is your inflow that we have given here, this is as inflow. After substitution and the simplification, you can say this will come like this, dou rho u dx dy dz y dou z here. And similarly, rate of increase in mass in y direction, it will be simply dou rho v dx dy dz by dou y. Why dx dy dz we have multiplied here? Because this is a per unit volume. So, you have to multiply it by volume also. So, it will be coming like this. So, dx dy dz. So, this one rate of increase in mass in z direction, then it will be what is that? Similarly, dou rho w dx dy dz y dou z. And total rate of increase in mass, then it will come dx dy dz after simplification into dou rho u by dou x plus dou rho v by dou y plus dou rho w by dou z, that will be equals to what? 0, because there is no storage of mass of fluid in this particular section, that is called at steady state operation. We are considering as per mass conservation law, that simply you can write this. Now, from the law of conservation of mass, then total rate of increase in mass should be 0. So, that is why we have written here it will be 0. Therefore, after simplification we can get this dividing by this volume dx dy dz, we can get this equation. Now, these equations will be applied for compressible and incompressible, but for incompressible fluid this rho should be constant, So, that is why after cancellation of this rho or dividing by rho in the both sides, then it will be coming like this. So, for incompressible flow, since rho is constant, we can get simply dou u dou x plus dou v dou y plus dou w dou z is equals to 0. Whereas, for compressible flow, you cannot segregate this rho u rho from this rho u here derivation, you cannot segregate, because this rho will be changing with respect to x there and y and z also. So, you have to consider this rho u here and derivation. So, this is applicable only for this compressible flow, whereas for incompressible flow the rho can be omit out and then it will be like this. So, this is called 3-dimensional continuity equation. Now, what should be that 2-dimensional? You can easily derive this 2-dimensional continuity equation from this 3-dimensional flow. If you know this dou u dou x plus dou v dou y plus dou w dou z for 2-dimensional flow, this if you w will be equals to 0, suppose in the z direction there will be no flow, then in that case w will be equals to 0 and hence dou w dou z will be equals to 0, then simply it will be dou u dou x plus dou v dou y will be equals to 0. So, this is your 2-dimensional continuity equation, and this is for incompressible fluid, and for compressible fluid then it will be rho u by dou x dou rho v dou y, that will be equals to 0. Here again then you have to consider that density. And let us do an example here. Let it be here the velocity distribution for a 2-dimensional incompressible flow is given by, suppose u will be equal to what is that, ln x square y square minus 4 into ln x t, then v will be equal to 2 y by x plus 4 ln x t. So, this is your example, and in this case you have to check whether this velocity distribution in the u and v direction, whether combination of this velocity distribution will follow this continuity equation or not. So, in this case simply you have to calculate, you have to find out what will be the dou u by dou x from this u is equal to ln x square y square minus 4 ln x t, then you will get it will be minus 2 x by 2 by x. Similarly, dou v by dou y you can calculate it from the velocity distribution in the y direction, then you can get it again plus 2 by x. So, summation of these two, what it will come? It will be coming 0. So, as per 2-dimensional continuity equation, you can have this as per your example, it will be 0 based on your velocity distribution. So, this velocity distribution will follow this continuity equation. Another examples, whether this 3-dimensional flow will follow the continuity equation or not. Let it be given that in the x direction the velocity distribution is u, and this in the y direction the velocity distribution is v. Now, find the missing component of velocity, so that the equation of continuity for the incompressible fluid will be satisfied. So, in that case, very interesting that we know that the 3-dimensional continuity equation, in that case it should be equals to 0, summation of this velocity gradient in all directions it will be 0. Then in this case we are getting only 2-dimensional distribution, velocity distribution u and v, but z direction is not there. So, to find out the z directions and to follow the what is that continuity equation. So, we have to consider that there will be certain velocity in the z direction. So, in that case z direction velocity, let it be w. So, dou u dou x plus dou v dou y and plus dou w by dou z should be equals to 0. In this case u, since it is given, so dou u by dou x will be equal to what? After derivation it will come 4 x plus 2 y, whereas v is given to you. Accordingly, if you do the derivative of this v with respect to y, you can get dou v dou y, then you can get finally 3 z square. Now, you know this, then 2 dimensions here u and v directions, what will be the velocity gradient, remaining one is required, dou w dou z is not known to you. So, from this continuity equation you can simply, after substitution of these the component this one that is dou u dou x, dou v dou y, and remaining dou w by dou z will be remain same. Here you have to find out it is not known to you. So, since these are known, this is known and this is unknown, and it will be, of course, it will be equals to 0, and after simplification then dou w dou z, that will come minus 4 x minus 2 y minus 2 z square here. So, from this equation if you integrate it, what will happen, then you can get it w will be equal to minus 4 x z minus 2 y z minus 2 by 3 z cube some plus constant here. So, after integration you can get this w. So, w, that is the velocity distribution in the z direction. So, velocity distribution in the z direction, this will be your final equation. Now, if we consider this final equation of this velocity distribution in the z direction and u and v, and reverse calculation of this dou u dou x and dou v dou y and dou w by dou z, you will see it, you can get it as that is simply 0. So, that is why continuity equation will follow, and as well as you can find out the remaining velocity component if your at least 2 dimensional velocity distribution known to you. Another example, suppose a 2 dimensional velocity field is given to you, where in this case it is given u is equal to minus k y by x square plus y square, and v is equal to k x by x square plus y square, where k is a constant. So, in this case does this field velocity satisfy the incompressible continuity equation or not. So, in this case same way you just simply calculate what should be the 2 dimensional continuity equation. In that case w dw will be equals to 0. So, only du y dou u dou x and dou v dou y you have to calculate. Dou u dou x from these equations, what will be the after derivation, it will come like this 2 x k y by x square plus y square whole square, and whereas dou v dou y it will be coming as 2 y k x by x square plus y square whole square. So, these two terms are equal. So, it will be cancelled out, finally it will come 0. So, that is why this 2 velocity field will follow this continuity equation. Another example, a compressible steady flow pattern is given by u will be equals to this and w is equal to this. Here in this case in the x direction and y direction velocity component is given to you. What should be the y directional velocity component or velocity distribution equation, that you have to find out from the continuity equation. So, in this case the continuity equation will follow. Here this one is given to u and this one is given to u. So, what should be this this one. So, this one from the velocity distribution in the x direction you can find out, this will be your what 4 x cube, and this will be your what minus 3 y. So, remaining is dou v dou y. So, dou v dou y, that will be equal to 3 y minus 4 x cube, and after integration you can get it. So, simply this is also same way you can calculate what should be the continuity equation, and finally you can get 0, and what should be the velocity distribution in the y direction. So, this is the example you can. Another example like is certain 2 dimensional shear flow near a wall as shown in figure here, and has the velocity component like u is equal to u into 3 y by a x minus y square by a square x square, a is a constant and u also is constant here. So, derive from the continuity the velocity component in the y direction, assuming that u will be v will be equals to 0 at the wall, y is equal to 0. So, in this case again that continuity equation in the 3 dimensions will follow, and you have to calculate the dou u dou x from these equations. U is equal to this, what it is coming, it will be coming minus u into this like this, and then what is that in the z direction it is 0. So, what will be the in the u directions, that you have to find out from this. Finally, you can get is dou v by dou y, that will be equal to minus dou u by dou x, that will be equal to this, and then what is that, finally after integration you can get v will be equals to this. Now, what should be that v at what is that is given v is equal to at x and y is equal to 0. So, in this case u at that u 0, that means here at 0 minus 0, in that case y, if you are substituting this y is equal to 0 and v is equal to 0, in that case simply you can get it, u will be equals to here 0 and f x will be equal to some value. So, finally, you can get this v x 0 will be equals to what is that 0 and f x will be equals to 0. So, final equations will be equals to here f x will be 0. So, finally, v will be equal to what this one. So, this velocity component. Now, this velocity component very interesting that here it is coming u into 3 y square by 2 a x square minus 2 y square by 3 a square x cube. So, this is totally different from this u. Now, again if you do this derivative of u with respect to x and this v with respect to y and sum it up, you will get 0. So, that is why this continuity equation will satisfied. And so, very interesting that from the continuity equation, if you know the velocity field in particular directions, then remaining directions what should be the velocity component you can find out from the continuity. The only thing is that the gradient of the velocity in x, y and z directions summation, their summations will be 0. So, we have discussed the continuity equation. This is in 1 dimension, 2 dimensions, 3 dimensions, and also how to derive those continuity equation in all directions also, and what should be the fact in that case, how actually we can calculate the velocity distribution in either directions with an example. And I think you can go through these examples again and try to actually assess yourself by considering different value, the cross sectional area, event velocity distribution, and following the other textbook also, you can I think will learn and you can understand easily. So, thanks for all today. Thank you for attention.